Chapter 14, Energy Method, Strain Energy in Shafts. We want to derivate strain energy due to different loading like axial force, mhm, which leads to ends up in normal stress. That's U sigma. Shearing stress, that's U tau. Torsion and bending moment. So they are one, two, three, and four situation for calculation of four different condition for strain energy. So as we know, strain energy is if you draw stress versus strain, mhm, the area under a stress strain diagram is strain energy density. This area just show us the energy density, and we show that by u lowercase u, and that's a half of that's a area of this triangle, and that's half of sigma stress times strain. And from Hooke's law, we do know sigma is equal to modulus of elasticity times a delta. mm, Stress is equal to E times strain. And if you replace delta is sigma over E, and if you replace this delta in this equation, it just gives you a U lowercase, which is strain energy density is equal to a half of sigma squared over modulus of elasticity. Mhm. And if you want to know what is the capital U, you just simply multiply the density of energy times the volume, mhm, of your ship, whatever it is. And then U capital is just if you just replace, and sigma is just a force over an area, so you can show the strain energy in terms of force and stress as well. So that's a in terms of force, that's a p squared times length of your shaft over 2 times E times area. Mhm. So let's see if we have a two circular shafts attached to each other, and at the end there is an axial force of P applied to point C of our configuration. And each part has the length of L over 2, so their length are equal, but the area of the first part is just A, and the other one is N squared times A. And N can be 1, 2, 3, 4, whatever. So in that case, UN is equal to, if if you just calculate it for different kind of n, un is equal to p squared times l over 2 times 2ea plus the second part, that's for the a to b, mm, that's the u for a to b, and the other part is p squared times the other half over 2, this time n2 n squared times area in parentheses times modulus of elasticity. And if you simplify that, it just gives you p squared times L over 4EA. You just take it to the denominator times 1 plus 1 over n squared. Mhm. Yet if you simplify it more, it just gives you a coefficient times p squared L over 2EA. So if you calculate, the interesting part is if you calculate it for U1, mhm, it just gives you, if you calculate it for U1, it just gives you, let's go by this color, it just gives you a p squared times L over 2EA. If you do the math for U2, it's a 5 over 8 times p squared L times 2EA. Likewise, U3 is 5 over 9 times U1, and U4 17 over 32, U1 and U5. So if you just call this like this, or U1 if you call it the unit, mhm, the other U2 is just a 62% of U1, U3 is 55% of U1, U4 is 53%, U5 is 52. You can easily see how U is decreasing, but it just there is a drop from 1 to 2, but then the incremented there is the incremental decrease, and they are reducing in size from U1 to U2 to U3 to U4. So the increment are decreasing. Mhm. So U1 is again p squared times L over 2EA, times a 1 plus n squared over 2n squared. So note 1 is for n greater than 1, un is equal is smaller than u1, as we observed that in previous slide. So u1 was a unity, and u2 is a 62% of that, u3 is a 55%, so it's decreasing. For as you increase the cross-sectional area for the second part, it just decreases or reduce from the when n is equal to 1. Mhm. The other interesting part is that maximum stress occurs in portion BC, because we do know sigma is P over area. So if n is increasing, mhm, so the maximum stress happens here. So that's a minimum area, which is from part, this is the area, and that gives us sigma maximum. So maximum stress occurs in portion BC of rod, and it's equal to sigma maximum P over A. Then for a given allowable stress, increasing the diameter of portion BC of the rod, if we increase the diameter of or cross-sectional of this part, it just decrease it just decreases the overall energy absorbing capacity. That's why unnecessary changes in cross-sectional area should avoid in the design, especially in the practical concern, which is in the practical example, which engineering example, which energy absorbing capacity, like impact or momentum problems, a that's a concern. Mhm. Let's that was the calculation and an example of a strain energy due to normal for the first scenario. Let's consider the strain energy due to shear. So we do know that a U for shear, so lowercase u density of strain energy under shear condition. This time Our normal, our vertical is a shearing stress, and a x-axis is just a gamma. If you remember that, uh, now this area is the triangle, a half of tau times gamma, and again from the Hooke's law in shear, tau is equal to g times gamma. Mhm. And if you replace that by gamma is tau over g, and then density of energy in shear is a half of tau squared over g. Mhm. So it means if you have a vertical force applied at C, mhm, and then capital U, which is the strain energy, is a strain energy density times volume. Mhm. And if it's a continuous, for example, shape, it's integration or of tau squared over 2g dv. And if it's something like separated part, you need to summation of something like tau squared over 2g for first part plus etc. Mhm. So again, strain energy due to shear is the integration of tau squared over 2g dx. And this third scenario is the condition which we have for a torsion. If a torsional torque applies at the end of C, and we do know the shear uh, introduced by a torsional torque, that's a torsion times C over J. Mhm. So this is the radius, mhm, R or C, and J is polar moment of inertia. Mhm. If I'm not wrong, that's a 1 over 2 pi r squared J for a solid circle. Mhm. That's polar moment of inertia. Mhm. And then if you just replace that in the formula, U is equal to integration of t squared over 2gj dx. Mhm. That's a torsional torque. So if you have a combination of different discrete parts attached to each other, un is t squared times L over 2 if both parts are L over 2 times 2gj plus, that's for, this is for BC, and for part AB, that's a t squared times L over 2, this time 2 times n to the power of 4 times j, because j is a half of pi r or c to the power of 4. That's why we have n4. And that's equal to t squared times L over 4gj times this time 1 plus 1 over n to the power of 4. Hmm? So again, if we want to observe it, that's the strain energy for this condition. If you have if you have, for example, two discrete part and the other part is n2 squared and n is 1, 2, 3, etc. U1 is t squared L over 2gj. U2 is 17 over 32 7 U1. Likewise, U3 is 89 over 178. And if again, if you defined U1 as a unity, T2 is 53% of U1 and U3 is just 50%. You can see the trend, and that's interesting. You can also make a comparison for a strain energy due to torsion with strain energy due to axial force or normal stress. Mhm. And just think about the strain energy due to bending moment if we have the same configuration and a bending moment apply at the very end. So if you have a load P, just think about uh, this condition, and if you have any idea or any interesting discovery or any answer or question, I would be very happy to hear and look at your solution in the comments. Thank you. We'll solve more problems on strain energy in chapter 14 for energy strain energy in beams and shafts. Thank you.